So the basic equation, we can actually see this heat generation terms also comes into picture. And using the boundary conditions, we have actually derived the temperature profile within. Okay. And we actually saw that now the temperature profile is actually not linear or something. It is actually going to be parabolic. Okay. And then we actually said that the heat flux also, it is now a function of x. It is not independent of, it is not constant throughout. And we said that if the boundary condition is actually same on both sides, if the boundary condition is actually symmetric on both sides, and the heat generation is actually constant throughout. So in that case, the temperature profile within is also going to be symmetric about the center axis. And therefore, we actually said that the center line, we can actually assume it as a symmetry line, and we can actually give the give the boundary condition dt by dx is equal to 0. Yeah, and then we actually went on to see the variable thermal conductivity. So we said that the thermal conductivity in many of the conditions is actually a function of temperature itself. Okay, but rarely in some systems it might be actually function of position also. It is actually happens mainly for liquids and solids and all, liquids and all. But in solids and all, it's actually very rarely it is actually going to be a function of location. Okay, but in these cases, we can see that it is actually a function of temperature. So therefore, we need to actually take into consider this temperature variation of conductivity also. But in many of the cases, if you want to actually consider the effect of conductivity itself, then we can see that it is actually all going to be very difficult. Okay. So in the basic equations itself, we can see that everything is actually going to be very difficult. Okay. The basic equations everywhere, we need to actually now consider the k as a function of t itself. Okay, since it is actually varying, so we cannot actually take k outside. So it is actually going to be very much difficult for us to deal with. Okay, so therefore, what we are actually saying is, okay, instead of taking k in the variation of k itself, we are actually trying to find an average k, and we actually said we can actually derive one average k. Okay, which we can actually see that it is actually the temperature average k. K average is equal to integrating kt dt divided by t minus t1. So for that, we need to actually find the k as a function of temperature itself. So we can actually express that. So in many of the conditions, in the temperature range, we are actually dealing with the temperature profiles are almost linear. Uh, okay, so that's what we actually saw. Yeah, here we actually saw that for suppose if we are actually talking about 100 or 200 degrees, so in many of the conditions it is actually a function of it is actually varies mainly linear with the temperature. Okay, so obviously if you are actually taking from zero a range of 1,000 degrees or something, then in that case it may not be actually varying linearly all the time. Okay, but in many of the conditions, practical conditions, we need maximum 200, 300 or 500 degrees. In that case, we can actually assume the variation to be linear, and we can actually give the equation k0 into 1 plus beta t. So if you actually average that, then we can actually get some average thermal conductivity. So any doubts still here?
No,
Any
sir.
doubts? Yeah.
No, sir.
So we will see the example for or practice problems for heat generation and or maybe next tutorial. Okay, this week or next week we will see that. Okay. So till now we were actually talking about the Cartesian systems. Everything was actually fine, and we got some nice equations, expressions, and all. But we are actually going to see steady state 1D conduction in cylindrical systems. Okay, steady state 1D conduction in cylindrical system. In cylindrical system. Okay. First, we are actually going to see without heat generation. Okay. Then we will actually see with heat generation. without heat generation. Okay. So in the radial system, the 1D conduction, what we are actually seeing is in a radial system, we know we are actually having r theta as well as length direction. We can actually call it as z. Okay. So here, what we are actually saying is the variation is actually only along the which direction in most of the condition we can actually consider. Variation is actually mainly suppose if you are actually having a tube like this, okay, a solid cylinder, hollow cylinder, we can actually say. So we are actually having a hollow cylinder like this. What we are actually saying is through inside we are actually having a fluid T and T infinity. Okay, and outside we are actually having H2 and T infinity 2, T infinity 1 and T infinity 2. Okay, so which direction do you think a thermal gradient is actually going to, a temperature gradient going to be? So mainly in the R
R
direction.
direction.
Yeah, very good. So in the R direction, this gradient is actually going to be there. Okay, so basically we can actually have a temperature in Z direction as well as theta direction also. But here what we are actually saying is the gradient in R direction is actually higher compared to that of theta and Z direction. Okay, so in many of the practical problems also we can actually have. Okay, so therefore that's what we are actually considering. Considering we are actually considering temperature temperature uh, gradient in radial direction is actually higher. Radial direction of cylinder, radial direction of cylinder is much higher than gradient in azimuthal and azimuthal or circumferential, azimuthal and axial directions. Axial direction. Okay, so therefore we are actually considering T as a function of TR. An example is actually we can actually say heat exchanger. We will see heat exchangers in detail later. And heat exchanger, what happens is that we are actually having a fluid flowing inside and a fluid flowing outside. Usually outside the temperatures might be actually higher, and but again we can see that along the length the temperature might be actually vary, but we can actually the variation of temperature along the length is actually much lower compared to that of temperature gradient within. Okay, so that is actually one example for this. So in that case we can actually consider the temperature gradient only in the radial direction. Okay, so mind it, always there is actually going to be gradient in z direction. So gradation in temperature in azimuth direction or circumferential direction is actually very rare, and it is actually very difficult to analyze also. Along the length there are actually much conditions are actually there, that also we will actually see flow through pipes and okay. But in radial direction in steady state 1D condition we are actually assuming that variation is actually less compared to that of the radial direction. Okay. So one example is actually the heat exchanger. In heat exchanger, we can actually know that heat enters at T1 and exit at T2. Okay, Ti1 and Ti2 and all fluid. For example, the outside also temperature maybe actually at the inlet it might be T out 1 and at the inlet T out 2 and all. So, but in our favor, we can actually average these temperatures and say the temperature on the outside or inside, it is actually going to be Ti. It is actually the average of Ti1 plus Ti2 by 2. Likewise, for outside also, we can actually say TO1 plus TO2 by 2, kind of an average temperature. Okay. Then if you are actually assume that the full internal surface, it is actually temperature Ti, and full outer surface, it is actually going to be at temperature TO2. TO. Okay. So that is actually our analysis actually going to be. So in that case, we can actually assume temperature to be constant throughout. Okay. Yeah. So our system is actually going to be like this. Okay. So mind it, my drawing is actually not that good. Okay. Okay. So this is actually going to be our cylinder. Okay. So this is actually our cylinder. Yeah. Okay. So we are actually considering a hollow cylinder over here. So we will actually see why we are actually considering hollow cylinder. First of all, it is actually of engineering importance. And its a radius, we are actually saying it is actually R1 and R2. Whereas the internal surface temperature, we can actually call it as T1 and T2. Okay. So T1 is actually constant throughout, T2 is actually constant throughout. And we are actually considering the length of the cylinder to be L. Length of the cylinder to be L. Okay. So now assuming temperature gradient only in R direction, temperature gradient only in radial direction, we can actually say T is equal to T as a function of R. Okay, so it is not a function of theta or something. And since we are actually talking about without heat generation, can anyone say our basic governing equation? Where did we actually derive that? Yeah. So from this, can anyone say what is actually going to be our governing equation? Yeah, from here. From 8, can anyone say what is our governing equation? Can you all hear me?
Yes, sir.
Yeah. So can anyone say the governing equation? So we said we are actually having gradient only in the radial direction, right? So is there any term with dou by dou theta or dou by dou z?
Sir, those will be zero, sir.
Those will be actually zero, and there is no heat generation, and there will be no temperature gradient. Okay. So therefore, we can actually write only the first term in this equation will be actually retained, right? So we are actually going to write 1 by r d by dr. Instead of dou, we are actually writing d. Kr dt by dr is equal to 0. Okay. So that is actually going to be our governing equation. Okay. And we are actually assuming k to be constant. Assuming k as constant, we can actually take k out, and also we can actually multiply this r. We can actually take this r also to this side. So therefore, we can actually write as d by dr into r dt by dr is equal to 0. Can anyone integrate it for me? Okay. So integrate once. Integrate once. What we are actually getting if we are integrating once?
R dt by dr equal to C.
R dt by dr is equal to C1. Okay, we can also write it as dt by dr is equal to C1 R. Okay, yeah. C1 by R. C1 by R. Okay. So we are actually integrating again. We can actually take this dr over here. So we can actually take this dr over here. And if you are actually integrating again, what we are actually going to get? Integrating again. Integrating again. What are we going to get? What is
C1 ln R plus C2.
yeah, very good. C1 LNR plus C2. Okay. So this can be actually numbered as 25. And what are actually the boundary conditions? Boundary conditions. R is equal to R1, T is equal to T1, R is equal to R2, T is equal to T2. Okay. Yeah. So now we are actually going to check what is actually going to happen. So yeah, here itself we can actually see that suppose if you are actually talking about a solid system, if you are actually talking about a solid system, then is there any chance that R is equal to 0? If you are actually solid cylinder, if you are actually considering, then obviously there is actually point where R is actually going to be 0. And the equation whatever we are actually deriving, it is actually applicable for the full geometry we are talking about or full control volume we are talking about. Okay, and this R is equal to 0 is actually included in that. So in that case, we can actually see that C1 ln R is equal to ln 0 is equal to, it is actually undefined. Okay, so in order to make that happen, we need to actually make ln as even as 0. Okay, so in that case, we can actually see that T is actually a constant only. So therefore, the first thing whatever we are actually getting from equation is that in order to achieve a steady state condition without heat generation and heat storage, there is no heat storage and heat generation, right? We cannot actually achieve it in a solid condition because here you can actually see that E in plus E generated is equal to E stored plus E out. Okay, so we are actually saying there is no heat generation and we are actually saying there is no heat storage. Okay, if R is equal to 0, if R is equal to 0, then there is no heat addition. There is actually no provision for heat addition at the inner surface. Okay, so therefore there is no E in is equal to 0. So therefore there will not be any E out also. So therefore the temperature whole thing need to be actually constant. So other option is that on one side here we are actually saying some heat addition is there. From the other side we are actually saying and heat rejection is there. So in that case it is actually okay, but again this circumferential variation of also comes into picture. So in that case, it actually goes to be a 2D conduction. Okay, yeah. So that's what it is actually about. So from this equation itself, we actually got the inference that the steady state, in order to happen the steady state, E in and E out are actually required. For a solid cylinder, E in is actually not possible, or E out is actually not possible. Okay, yeah. But we will actually see that if we are actually having a heat generation, if you're actually heat generation, that's what we will actually see in the next section. If you're having a heat generation, then even though there is no heat addition, we can see that whatever the generated can be actually get out. Okay, so in that case we will actually analyze for a solid cylinder. Okay, so anyway, we can actually solve for the temperature profile over here. We are actually putting our conditions into boundary conditions in 25. If you're actually doing that, then you will get T1 is equal to C1 ln R1 plus C2 and T2 is equal to C2 ln R2 plus C2. Okay, C1. Okay, so we can actually, there is actually two equations and two unknowns. I'm not going to solve it. I'll just give the values. C1 is equal to T2 minus T1 divided by ln R2 by R1. Okay, we are actually saying we can actually call it as A and B. So we are actually saying B minus A. B minus A. If you're actually doing B minus A, you are actually getting this. Okay. Now putting now put C1 in B. If you're actually putting C1 in B, then you will be actually getting C2. C2 we can actually call it as T2 minus T1 divided by ln R2 by R1 into ln R2. Okay, so therefore we can actually see that T is equal to T2 minus T1 divided by ln R2 by R1 into ln R plus T2 minus T1 divided by ln R2 by R1 into ln R2. Okay, so we are just rearranging it a little bit. We can actually take T2 minus T1 by ln R2 by R1 as common. T2 minus T1 divided by ln R2 by R1. We are actually taking it as common. So in that case, we can actually write ln R minus ln R2. Okay, so since we are actually having minus, we can actually convert it as a ln R2 ln of R by R2 plus T2. Okay, so we can actually call it as 26. So this is actually the temperature profile variation within the cylinder. Okay, so we can see that it is actually a function of ln R. Okay, so is that clear? So there is actually one more equation we can actually write here. We actually put C2 or C1 in equation B. C1 in equation B. If you're actually putting C1 in equation A, we are actually getting the temperature in terms of T1 and ln, T1 and R1. Okay, so that also is actually the same thing. We will actually get in that case T1 minus T2 divided by ln uh, R2 by R1. You can actually try that. Okay, ln R by R1. So what we are actually getting is equal to T1 minus. We can actually call it as 16A. Okay, yeah. So anyway, these two equations we can actually see that these are actually the temperature variation inside the cylinder. We can say it is actually logarithmic. Okay, it is actually not constant for a valve. We actually said that it is actually the temperature variation is actually linear or linear temperature profile LTP. But for a cylinder, we can actually see that it is not linear, it is actually going to be logarithmic. Okay, so that means if it is actually T1 and this is actually T2, it is actually going to be varying something like this. It is not going to be linear. Okay, so not that temperature profile is temperature profile is logarithmic. Okay, logarithmic. Why it is so? Why it is so? Because this is actually due to the varying temperature, varying area at every location. Okay, so this is actually the direction of movement of the heat flux, right? The heat is actually traveling in this direction. So you can actually see that at every location, the cross-sectional area is actually increasing. Okay, the cross-sectional area is actually increasing. So that's why we are actually going to have this varying temperature. So since the cross-sectional area is actually increasing, and we can actually see that the temperature, the heat flux, okay, heat is actually going to be constant, but heat flux is actually varying. And we know that Q is equal to heat flux is equal to minus K dt by dx. Okay, so minus K dt by dx, we can actually see that heat flux need to be actually varied. Heat flux is Q by A. Q by A is actually the heat flux. We can see that heat flux is actually varying throughout from inner radius to the outer radius. Okay, and we can see that heat flux is actually directly proportional to the temperature gradient. Since heat flux is actually varying throughout, then the temperature flux or temperature gradient also should vary throughout. Okay, so that's why we are actually going to get a logarithmic profile. Okay, so this is due to varying cross-sectional area, varying cross-sectional area, varying cross-sectional area along radial direction. Okay, yeah. So again, from this profile also, we can actually see that when R is equal to 0, then everything is actually going to be exploded. Okay, so when R is equal to 0, ln R by R0, ln 0 is actually undefined, so we cannot actually go for. Okay, that also we can actually write equation 26 breaks down when R is equal to 0. Okay, so that means for a solid cylinder, a steady state conduction is actually not possible. Okay, so for solid cylinder, steady state steady state conduction, heat conduction, steady state heat conduction in radial direction is not possible. Is not possible. Okay, not possible without heat generation. Without heat generation or storage. Or storage. Without heat generation or storage. Okay. Why? Because we are actually saying E in and E out are required as E gen is equal to E store is equal to 0. Okay, so we need to actually have provision for heat inside, heat in and heat out. Okay, so now we are actually going to see what is actually the heat transferred through this. So we are saying that heat flux is actually a function of temperature. Heat flux is actually a function of radial distance. But we know that the total heat should not be actually a function, right? So whatever the heat actually get in, it should actually get out. So heat flux is actually a function, but total heat transfer Q into Q, total Q, that means heat flux into area, it should be actually same throughout. It shouldn't be actually varying because we are actually talking a steady condition in which heat in is equal to heat out. Okay, heat in at a inner radius should be actually equal to heat out. Okay, so that's what we are actually going to find out now. Now heat transfer at any location we are actually going to find. Now heat transfer at any location R. Okay. So how we can actually find? We are actually saying Q is equal to minus Ka dt by dx. Here we are actually talking about the total heat. Okay, not flux. It is actually the total heat. So how we can actually write minus K? What is actually area at any particular radius? What is actually the area at any particular radius? Cross-sectional area at any particular radius. So here what we have to actually find is what is actually the total area at any particular radius. Okay. So what is actually the area for this? We are actually saying heat is actually passing in this particular direction, perpendicular to that. What is actually the area for this surface?
So 2 pi RL.
Very good. 2 pi r into L. Okay. So therefore we can actually write 2 pi r L into dt by dr. Okay. So this is not dx, it should be dr. But what is actually dt by dr? Obviously, we can actually differentiate it over here and we can actually find. Luckily for us, we have already find here what is actually dt by dr. Dt by dr is equal to C1 by R. Okay. Obviously, from here also you can actually differentiate it and you will get say because dt by dx of ln r is equal to 1 by r. Okay. So therefore, we are actually getting this can be actually written as Q is equal to minus K 2 pi RL into we can actually write T2 minus T1 divided by ln R2 by R1, right? So this is actually dt by dr into 1 by r. Okay, C1 by r is actually our dt by dr. So here you can actually write, you can actually cancel this r off. So therefore, you can actually write. I'm just rearranging it. Here we are having a one negative sign, and I'm actually taking inside. So you can actually write 2 pi kl T1 minus T2 divided by ln R2 by R. Okay, yeah. So that is actually the total heat flux. So is this a function of R? is a heat flux.
No, sir.
Yeah, it is. It shouldn't be. Yeah. So that's what we actually said. Total heat is actually not a function of R, but
No,
heat
sir.
flux is actually going to be function of R. Okay. So therefore, you can actually see that Q is independent of R. Independent of R. Independent of R. Whereas heat flux is dependent on R. Dependent on R. Okay. Yeah. So we can actually write this as actually 27. Okay. Can we actually write or can we actually have further analysis on this? So anything similar we have actually seen for Cartesian system? We can actually write as 27 can be also written as Q is equal to T1 minus T2 divided by L1 R2 by R1 divided by 2 pi Lk. So what we have actually, why we have actually written over here? Because it is actually similar to T1 minus T2 divided by R. Okay, what is actually this R? What is actually this R?
Resistance.
Thermal resistance.
Yeah, very good. Thermal resistance. Okay, so here also you can actually see that we can actually write the Q or heat transfer as well as the thermal potential in the electrical analogy. Okay, so therefore, yeah, for this thermal for this cylindrical system, without heat generation and without heat storage, we can actually use again the thermal resistance analogy. So what is actually thermal resistance over here? So thermal resistance in radial conduction is, so therefore we can actually write R cylinder in this sense is equal to ln R2 by R1 divided by 2 pi Lk. Okay, yeah. So that's how we can actually, that is actually the resistance, thermal resistance for the cylindrical system for radial conduction. So now everything is actually going to be simple for us. Now consider convective heat transfer, convective heat transfer, boundary conditions, is actually the inner surface, and we can actually write it as the outer surface. So inside we are actually saying H1 T, we can actually say infinity 1, and outside it is actually going to be H2 T infinity 2. Okay. So that's what we actually know. So therefore we are actually assuming that surface temperatures are actually T1 and T2, which are actually unknown. Only thing is that we know what is actually K is equal to Ka, we are actually can say, and the radius is actually going to be R1 and R2. Okay, so if you actually know these things, can we actually write the thermal circuit? Okay, we can actually draw like this. So over here we are actually having T infinity 1, and first we are actually going to have the thermal resistance due to the convection. Okay, so 1 by HA. What is actually A over here? It is 2 pi
R1.
R1 into L. Okay, we are actually assuming for L distance. Okay, so along the length, it is actually L, the same way we are actually said over here. It is having a length of L. Okay, so 2 pi R1 L. So after that, it actually comes to T1, and after that, we are actually going to have the conduction resistance. Conduction resistance is L1 R2 by R1 divided by 2 pi Lk. Okay. And after that, we are actually going to have the outer temperature T2. After that, again, we are actually going to have the convection resistance 1 by H into 2 pi R2L into T infinity 2. Okay. So here you can actually see that outside the surface area or convective heat transfer area is actually 2 pi R2L. Okay. So you can actually directly write Q is equal to T infinity 1 minus T infinity 2 divided by R total. Okay. 1 by H into 2 pi R1L plus ln R2 by R1 divided by 2 pi Lk plus 1 by H into 2 pi R2L. Okay. Yeah. So that's how we can actually use the thermal resistance contact over here. So in case for a composite cylinder, for a composite cylinder, okay, so again the same thing we can actually use for a composite cylinder. That means cylinder with a different material. Okay, cylinder with a different material. Okay, so it is also known as a multi-layered cylinder. Okay, composite cylinder or multi-layered cylinder. So how does that actually look like? So inside we are actually going to have a inner circle. Okay, it is having some thickness, so it actually radius moves from R1 to R2. Okay, and outside that we are actually going to have another material. Okay, we are actually going to have another material with the radius R3. Okay, we can actually write R1, R2, and R3. Okay, so this is actually the radius R1, R2, and R3. Okay, so it is having say conductivities of first material, inner material, it is having a conductivity of Ka, and outer material, it is having a conductivity of Kb. And inside, what is actually the condition? We are actually going to have a convective heat transfer with H1 and T infinity 1, and outside we are actually going to have H2 and T infinity 2. So here we are actually writing inner surface temperature T1, intermediate temperature T2, and outer temperature we can actually write as T3. Okay. Yeah. So that's how we can actually write. Yeah, if you're actually going for the thermal resistance circuit, obviously we are actually going to have over here T infinity 1, and the first resistance is actually going to be, we can actually write 2 pi R1L into H1, and after that we are actually going to have T1, and then radial conduction resistance due to the first material ln R2 by R1 divided by 2 pi Lk, and then second temperature. Then we are actually going to have the conduction resistance due to the second material ln. What is actually comes in the ln? What actually comes inside ln? Ln of R3 by R2, right? So R3 by R2 into 2 pi L KB. So 2 pi L KB is actually, L is actually same for both the resistance because the length is actually same, and in that case the resistance, the radius doesn't comes into picture. After that we are actually going to have a temperature T3, and then we are actually going to have the convective resistance here 2 pi R2 R2L into H2. Okay, yeah, so that's what we can actually write. So basically we are actually saying this is actually series resistance, so therefore we can actually write as Q is equal to T infinity 1 minus T infinity 2 divided by R total. This is actually the total resistance. Okay, so total resistance means it is actually a summation of all the series resistance. Okay, yeah. So one parallel thing that can actually happen is, I'm not going to discuss in detail. Parallel thing that can
Excuse me,
actually happen is, yeah, ask me.
sir. In the above expression, for the last one, it's R3, right? 2 pi R3 L into.
Yeah. Sorry. Yeah, very good. 2 pi R3 L into H2. Yeah, very good. Yeah. So therefore, if we are actually going to have two materials like this, okay, so inner we are actually going to have a material A, and over here material B, and over here material C. Okay, so in this condition we can actually write as a parallel system. Okay, so this is actually the parallel system, a chance for a parallel system in cylindrical systems. Okay, yeah. Uh, so this one again, we can actually, we are now going to consider that idea of overall heat transfer coefficient. Okay, so this one T infinity minus T infinity 2 and R total, it is also known as, it can be also written as UA T infinity 1 minus T infinity 2. Okay. We have actually seen this overall heat transfer coefficient, right? Where U is overall heat transfer coefficient. Okay, so U is overall heat transfer coefficient, overall heat transfer coefficient. Okay, its unit is watt per meter square Kelvin. Okay, so and here we are actually saying U into A, and which A we are actually talking about. There is, if we are actually talking about a slab, we were having only one area, only the cross-sectional area is actually constant throughout. Here we are actually having different areas. So which area you can actually use? We are having the inner surface area, outer surface area is there, even intermediate area is actually there. Okay, so which area we can actually take? Actually, we can actually take any area. Okay, you can be defined defined in terms of A1 is equal to 2 pi R1L, or A2 is equal to 2 pi R2L, or A3 is equal to 2 pi R3L. Okay, so any area you can actually say. So our calculation, we are actually trying to do it based on uh, so based on A1. Okay, based on A1 we are actually going to do our calculation. So based on A1 we are actually saying U1 is equal to 1 by R total into A1. Okay, U1 is equal to 1 by R total into A1. So it can be actually written as, okay, so we are actually assuming for unit length, for unit length, that is L is equal to 1. Okay, for our further calculation, we are actually not taking into consideration the L. So U1 is actually equal to 1 by R total into A1. So therefore, we can actually write as, what is actually R total? 1 by, so here 2 pi R1 L into H1. Okay, into A1 we are actually writing, plus 1 by 2 pi Lk into Ln R2 by R1 into A1, plus Ln R3 by R2 divided by 2 pi L Kb into A1, plus 1 by 2 pi R3L into H2 into A1. Okay, so what is actually A1? A1 is equal to 2 pi R1 into L. Okay, so that's what now we are actually going to cancel this A1 from the denominators. So therefore, you can actually write as 1 by what is actually over here? What will actually come over here in the first case? So 2 pi R1L, A1 is equal to 2 pi R1L. So we can actually cancel off that. So 1 by H1 plus, so here you can actually cancel 2 pi R1, 2 pi L in numerator and denominator. So it will actually come as R1 by Ka Ln R2 by R1 plus R1 by Kb Ln R2 by R3 by R2 plus R1 by R3 into 1 by H2. Okay, so that is actually U1. Okay, so that's how we can actually calculate the overall heat transfer based on U1. So instead of A1, you are actually going with A2. Okay, then you are actually going to get the another equation. So, but what you can actually see that, not that U1 A1 should be actually equal to U2 A2, and that should be actually equal to U3 A3. And likewise, if you are actually taking any radius or any area, so into that overall heat transfer coefficient, it will be actually same. So then only our equation, basic equation of U8 T infinity 1 minus T infinity 2 will actually satisfy, right? Yeah. So that is actually the thing, and we can actually write as 28. Okay. Yeah. So that's how you can actually make use of this thermal resistance analysis for the for the cylindrical system without heat generation. Okay. Yeah. So any doubts in here? Okay.
No, sir.
Yeah. Oh, no, sir, you said? Okay, I thought yes, sir. So now we are actually going to see another topic, which is actually derived from what we actually discussed over here. Okay. Yeah, which is actually discussed over here. It is actually known as critical thickness, critical thickness or radius of insulation. Okay, critical thickness of or radius of insulation. Okay. I am having a question over here. Okay, last time somebody actually asked me if you are actually having a insulation like this. Okay, so this is actually the pipe inside, and this is actually the some material. Okay, so this is actually R1, okay, and this is actually R2. I have one question over here. We are actually having a some material over here, right? So some material over here. So our understanding is that since we are actually having this material over here, we are having some resistance, right? So what is actually the resistance? Resistance is actually going to be ln R2 by R1 divided by divided by 2 pi Lk. Okay. So my question is that if you are actually having this material, if I am actually increasing the radius, okay, if I am actually increasing the radius for this one, does the temperature or does the total resistance is actually going to increase or decrease? I can actually make it simple. If we are actually having a slab, a Cartesian system I am actually talking about. Okay, Cartesian system I am actually talking about. So here we know L by Ka, right? So here, if I am actually going to increase the thickness, okay, so does this resistance going to increase or not? Does the thermal resistance going to increase or not? If I am actually going to increase the thickness, huh?
Yes, sir.
Yeah, it is actually going to increase. So here, yeah, for that is actually clear in a Cartesian system. It is actually going to increase. But in the cylindrical systems, this thermal resistance, is that going to increase or not? From the equation, you tell me. Ln R2 by R1, 2 pi Lk. If I am actually going to increase the resistance, is that going to increase?
Yes, sir. If R1 is like same, then if you increase the R2, then it will increase.
Yeah, yeah, very good. So we can actually see that these are conduction. Okay, so this is actually the conduction in which it is actually going to happen. Okay, so now consider the second one. So here, from here, we are actually going to have a convection also, right? So at the end of the slab, we are actually going to have the convection. So what is actually the convection resistance? 1 by HA, right? Yeah. So we can actually see that the cross-sectional area is actually constant in this case. So here, if you are actually increasing this length, okay, so is the convection resistance going to increase or decrease? You're actually going to increase the length. Is the convection resistance going to increase or decrease?
No effect, sir.
No effect over here because there is actually, it is actually doesn't matter. A is actually going to be constant. But in the radial system, you see, you tell me now, if I am actually going to increase the convection resistance, whether the conversion resistance going to increase or decrease. Okay, 1 by H into 2 pi R2L. The convection resistance going to increase or decrease. If I am actually going to increase it,
It will decrease.
it will decrease.
Decrease, sir.
So here we can actually see that the Q convection is actually going to decrease. Okay. So therefore, here you can actually see that simply increasing the radius of the system will not actually reduce the total resistance. Okay. So if you're actually taking only the conduction, obviously it is actually going to reduce. But since also the convection is also there, the total resistance associated with this system. Okay. So we are not neglecting, or we are actually not considering the thermal resistance in this system 0 to R1. First pipe we are actually not considering. Only the second material we are actually seeing. We are actually simply increasing the radius. The total resistance will not simply actually increase. Okay, so it will actually increase for some time. So that's what we are actually going to see. Since we are actually, so here two components are there. Our conduction is there and convection is actually there. So the conduction having the effect of resistance increasing, and our convection is actually resistance decreasing. So we are actually going to see what can we actually do with this. Okay. So in many of the conditions, we need to actually have an insulation also. So in some conditions, we need to actually transfer a fluid through a pipe, okay, without any heat losses. So we are actually saying that, okay, I'm actually going to add more and more insulation to that, so that heat loss is actually going to be less. Is that possible? Here we actually said that if I'm actually adding more and more insulation, I'm just simply increasing the R2. Okay, is that beneficial? So that's what we are actually going to see now. Okay, yeah. So yeah. So here this is actually the, so we are actually talking about the insulation. What is actually insulation? Insulation is actually nothing but a material with a very low thermal conductivity. Okay, so that's what we are actually going to write in cylindrical system. Okay, in cylindrical system, whatever we actually discussed, we are just going to write in cylindrical system due to varying area. Okay, varying area in the radial direction. Varying area in the radial direction, the total resistance, total thermal resistance, total thermal resistance, so will not, okay, will not always reduce with increase in insulation. Increase in insulation. Okay, then what is actually happening is what we are actually going to see. Okay, so although the conduction resistance increases, although conduction resistance increase with increase in temperature, increase with increase in thickness, is with increase in thickness, convection resistance decreases due to increase in outer surface area for convection. Okay, so that's what we are actually going to see now. Okay. So we can actually write our system as here the same system what we actually seen earlier. Okay, so we are actually going to have a material. So R1, radius R1 and R2. Okay, so radius R1 and R2. Okay, we are actually yeah, inner temperature we can actually say Ti for this surface, T1 for this surface, and T2 for this surface. Okay, because we are actually interested in the second material only. Okay, we are actually interested in the K insulation. Second material only we are actually interested, and here we can actually have T H and T infinity over here. Okay. So we are actually going to have a analysis for the second material, insulation material. So what we are actually going to say is our aim is to reduce. Okay, our aim is to reduce heat transfer between T1 and T infinity. Okay, so if you actually write the thermal resistance circuit, T1 we are actually going to have ln R2 by R1 divided by 2 pi Lk, and then we are actually going to have a T2, right? And then convective resistance is here 1 by 2 pi R2 into L into H. Okay, K insulation we can actually write. So here we are actually having T infinity. So now we are actually going to see at what point. Okay, so here what we are actually saying is, yeah, Q is equal to, we are actually saying T1 minus T infinity divided by, yeah, for unit length, okay, that means L is equal to 1. We are actually writing, we can actually write ln R2 by R1 divided by 2 pi K insulation. We are actually plus 1 by 2 pi R2 into H. Okay. So we are actually, what we are actually saying is there might be actually a radius in which the total resistance. Okay. So here the effect of conduction is actually increasing, resistance of conduction is increasing, and resistance of convection is actually decreasing. So what we are actually saying is that there is actually might be actually a value of R2, so that the total resistance might be actually going to be maximum. Okay, what we are actually saying is, okay, so as the R2 increases, okay, R2 increases, if this is actually R total, we are actually trying to see if there is actually a particular value where R is actually going to maximum. Okay, how can we actually find that? To find maximized R total, okay, so R total we are actually saying is equal to T1 minus T infinity divided by R total. So in this sense, R total is actually the summation of these two resistors. Okay, how we can actually find that?
Differentiate and equate to 0.
Yeah, differentiate with respect to
R2.
R2. Yeah, very good. R total is equal to 0. So that's what we are actually going to see. It is actually very simple differentiation. What we can actually say is, okay, ln R2 by R1. So we can actually differentiate it as 1 by R2, right? So therefore, it is actually going to give us 1 by 2 pi K into R2. Okay. So ln R2 minus ln R1. That's how we can actually write. So second time is actually going to 0. Okay. And first time ln R2 d by dx of ln R2 is 1 by R2. So we are actually getting this term. Okay. K insulation. So what is actually the differentiation for 1 by R2?
Minus 1 by R2 square.
Minus 1 by R square. Yeah, very good. So we are actually going to get minus 2 pi R2 square into H. So we are actually equating to 0. So we are actually cancel this 2 pi over here. and here R square is there, R2 is there. Okay. Yeah, better we can actually do it over here. Okay. Okay, yeah, is equal to 0. So therefore we can actually write 2 pi, or better write it like this: 2 pi K insulation into R is equal to 1 by 2 pi R2 square into H. Okay, so R square R2 is actually cancelled. So that actually gives us the idea R2 is equal to K insulation by H. Okay, so this is actually an important term. Okay, so R2 is equal to K insulation by H. So if we can actually put our R2 is equal to K insulation by H, we just said that the R total is actually coming to maximum. Okay, or is it? So that's what we have to actually see. So dt by dx is equal to 0. Yeah, we said that at R2 is equal to K insulation by H, something is actually happening. We are actually assuming it to be maximum total, but we are still not sure, right? So dt by dx 0, it can be actually maximum point or it can be actually minimum point also. So how we can actually find whether it is a maximum point or minimum point? Okay, we are actually going to find a second differentiation, and if it is actually maximum value, then we can actually see the second differentiation is actually going to be negative. And if it is actually minimum value, we can actually see that the second differentiation is going to be positive, right? Are you convinced with that? So I think you have actually studied that, right? Is that clear?
Yes, sir.
Yes, sir.
Yeah, very good. So that's what we are actually going to see. We said it is actually maximum, but we need to actually be sure of that. Okay. So to find if our total is maximum or minimum at R2 is equal to K insulation by H. Okay. We have to actually second differentiate it. Okay, so R total divided by D into R2 square. Okay, so that actually gives us, we have to similarly differentiate it whatever we actually discussed over here. So that actually gives us minus 1 by 2 pi K R2 square, then minus 2 over here. Okay, so plus 2 by nx raised to n minus 1, 2 pi R2 cube into H, right, is equal to 0. Okay, so now put at R2 is equal to K insulation by H. So here K means K insulation is there. So we can actually put R2 as the K insulation, and we can actually put do everything. So what we are actually going to get is so what we are actually going to get is 1 by 2 pi K cube by H square. Okay, so this is actually positive value or negative value? This is actually positive value. Okay, so what does that mean? This means that, so whatever we actually said, the R total R2 is equal to K insulation by H, that is actually going to be minimum at that particular point. It is not maximum. R total is actually minimum at the point where R2 is equal to K insulation by H. Okay, so whatever we actually said, or whatever the value we actually found for R2, that is actually the value at which R total is actually minimum. Okay, so this shows that at R2 is equal to K insulation by H, okay, total resistance is actually minimum. Total resistance is actually minimum. Okay, so minimum total resistance means what? So maximum heat transfer. Okay, so maximum heat transfer. Okay, so that is actually this radius. So if you actually plot a heat transfer across this, we can actually see that as R2 increases, we can see that the heat transfer actually increases, okay, and it actually goes to maximum at the point where K insulation by H. Okay, so this is actually the radius at which the lowest resistance occurs or the maximum heat transfer actually occurs. Okay, so therefore we can actually call this radius as critical radius. Okay, so the radius, so this radius is actually called as critical radius of insulation. Critical radius of insulation. Okay, so therefore, yeah, we can actually write RCR is equal to K by H. Okay, so this is actually written as 29, equation 29. So this is actually the radius at which we are actually going to get the maximum heat transfer. Okay, so therefore we can actually write below CR. Okay, so below CR, what happens if we are actually talking about the below CR, that is this range, as the radius increases, the heat transfer increases. Okay, and above the critical radius, as the radius increases, the heat transfer decreases. Okay, so therefore we should be also always be make sure that our radius should be actually somewhere in this region. Okay, our radius should be always somewhere in this region, so that further addition of the resistance or further addition of the insulation will always reduce our total heat transfer. Okay, so below RCR, Q increases with so Q increases with increasing R. Okay, and above RCR, Q decreases with increase in R. Okay, so increase in R. Okay, so why it is so? So why we are actually going to have is, in order to get a better picture, we can actually draw separately the R conduction and R radiation. Okay, so this is actually the R2, which is actually increasing, and this is actually the resistance we can actually see. So we said that as the R increases, what happens to the conduction resistance? Okay, so R increases, the conduction resistance, okay, increases like this. So this is actually the R conduction. So as the radius increases, obviously the conduction resistance going to increase. And what happens to the convection resistance? Convection resistance, it is actually lowest. When the radius is actually very less, it is actually having very low value. Okay, convection is equal to 1 by 2 pi R2L into H. Okay, when resistance is R is actually very less, yeah, I'm sorry. So this is actually the conduction is actually increasing. Yeah, conduction is actually decreasing, right? So this is actually conduction. Okay, conduction is actually decreasing, right? Conduction is actually decreasing. So R conduction, this is actually R conduction. Oh, sorry. And R conduction is actually increasing. R conduction is actually increasing. Okay, I'm sorry. So at a very low, very small R2, okay, we are actually having R as the R increases. So this thing. So at very low R2, we are actually having very high convection resistance. Okay, so since the R2 is actually very less, our convection is actually very high. So we can actually give it out here. Okay, as the R2 increases, our convection, we actually said it is actually reducing. So this is actually the R convection. I'm sorry for the confusion. Okay, so our convection is actually reducing. Okay, so what happens is that initially this reduction in the convection resistance overweights the increase in the conduction resistance. Okay, so therefore we can actually see that initially the total resistance, okay, the total resistance is actually reducing. So initially the total resistance is actually reducing. Okay, so and reduces in that, and it actually comes to a minimum point at R critical. Okay, R critical, it actually comes to a minimum point. So after the critical value, or after the R critical, the increase in the conduction resistance overweights the reduction in the convection resistance. So after that, the conduction actually increases, and it actually eventually comes up to the R conduction. Okay, so that's what it is actually going to happen. This is actually the R total. Okay, yeah. So this is what actually happens for this condition. So that's why we are actually going to have a critical radius. Okay, so this is due to the fact that at low values of R, at the low R till R critical, decrease in R convection overweights increase in R conduction. Okay, and above R critical, the reverse happens. Okay, that means the increase in the R conduction overweights the decrease in the R convection. Okay, yeah. So that point where the maximum heat transfer is actually going to happen is actually known as the critical radius. Okay, so therefore make sure that our insulation is always going to be at somewhere around, it is always going to be higher than that of the R critical. Okay, yeah. So, and also critical thickness. Okay, so critical thickness is actually nothing but TCR is equal to RCR minus R1. Okay, so that thickness of the insulation is actually known as the critical thickness of the insulation. Okay, but basically what we are actually finding is actually critical radius. From there you can actually find the critical thickness. Okay, yeah. Yeah. So that's how you can actually calculate the critical thickness of the system. Okay, but basically for insulation materials, usually they are having this uh, conductivity of somewhere around the 0.03 watt per meter Kelvin and all. Okay, and usually outside, now we are actually going to have a heat transfer coefficient of 5 meters square Kelvin. Okay, so these are actually the usual values, or even 10 watt per, or in the minimum condition, we are actually going to have a H of 5 watt per meter square Kelvin if you are actually going to have a natural convection. Can anyone calculate and tell me what is actually the R critical for this condition? Can anyone tell me what is actually the R critical for this condition?
Zero 0.006.
0.006. 0.006. What is that?
Meters.
Meters. Yeah. It is equal to, can we, how to convert to millimeters?
6 millimeters.
6 millimeter. Very good. Okay. So here you can actually see that for the regular conditions, okay, for the ambient condition, as well as for the condition in which a regular conductivity material, means insulation material, it is actually having a conductivity somewhere around 0.03. Okay. So in that case, we can see that R critical is actually going to be almost 6 mm. Okay, so that means it is actually very low value. So any of the pipe, any of the flowing fluid pipes, etc. So it is always going to have a diameters more than 10 centimeter or 20 centimeter like that. Okay, so in usual conditions, we don't have to actually so much worried about this critical radius, but because basically, okay, so the flowing fluid itself, so R1, Okay, so we are actually saying from R1 to R2, we are actually having the insulation. So usually R1 itself is actually going to greater than that of R critical. Okay, so therefore, whatever the insulation you are actually going to add, it usually gives or yeah, whatever the insulation you are going to add, it is automatically going to be added more to that of the critical radius. Okay, so in many of the usual conditions with insulations and all, you don't have to much worry about this critical radius, but you have to be actually know that there is actually critical radius which actually going to be acting or which actually comes into the play. Okay, yeah. So any doubts in this critical radius? Yeah, so everything is actually fine and good. I hope you actually understood everything now. So till now, how we are actually doing these things? So till now, in order to find the heat flux or the temperature profiles or heat flux as it is, our main aim is to actually find the temperature profile, then find the heat flux. Right? So how we are actually proceeding? We were actually writing the basic equation, right? And then using the boundary conditions, we are actually solving it, and we are actually getting the temperature profiles. Okay, and then differentiating the temperature profile, we'll get dt by dx. Based on that, we are actually calculating the heat flux and then further things. Okay? So it is actually very good method. That is actually how we can actually do this. But there is actually one more method in which we can actually do this. Okay? It's actually a simple method, which I just wanted to introduce that also too. Okay, so which says alternate method. Okay, method for calculation of Q and T. Okay, so this can be actually used for any system, for Cartesian system or cylindrical system or spherical system. Any system you can actually use this. Okay. So here, instead of going through the basic governing equations, so we are actually using the equation Q is equal to minus K dt by dx. Okay, so here we are actually solving it for cylindrical, but you can actually use it for cylindrical Cartesian system or spherical system or any systems. Okay, so here what we are actually saying is, we know Q cylindrical, it is equal to minus Ka dt by dr. Okay, so this is actually our basic equation, minus Ka dt by dr. A, we actually know that Q A is equal to 2 pi r into L at any r, 2 pi r into L. That is actually the cross-sectional area for the heat to pass in the radial direction, right? So now we are actually going to rearrange it. We are actually saying Q cylindrical divided by A, okay, into dr. Okay, into dr is equal to minus K dt. Okay, and we know that r is actually varying from r1 to r2. Okay, and t is actually varying from t1 to t2. Okay, we are simply going to integrate it. Okay, since we are actually going to have definite intervals, there is actually not going to be any integration constants or something. We are actually integrating from r1 to r2 and t1 to t2. So therefore, we can actually write, but a is equal to 2 pi r. Okay, we can write q divided by cyl divided by 2 pi l, okay, integral r1 to r2 dr divided by r is equal to minus k integral t1 to t2 dt. Okay, so we can simply integrate it. What we are actually going to get is q cylindrical divided by 2 pi l ln r2 by r1, because ln r2 minus l1 ln r1 we are actually getting l1 a minus b is equal to ln a by b. Okay, so equal to we are actually getting minus k t2 minus t1. Okay, so we can just rearrange it. We can actually write t1 minus t2. Okay, yeah, so therefore we can actually write q cylindrical is equal to 2 pi l, this is not r, this is actually l. Okay, 2 pi l k t1 minus t2 divided by ln R2 by R1. Okay, so this is actually same as equation 27. Okay, so equation 27, where is actually equation 27? Yeah, equation 27. Q is equal to 2 pi KL T1 minus T2 divided by ln R2 by R1. Okay, so how we actually made it? We directly integrated it and we actually got the solution. Okay, yeah. So that's how we can actually find the heat flux. Now we are actually trying to find what is actually the temperature profile. Okay, so but we know that the Q is actually same throughout. At any section, Q is actually going to be same. So since Q is the same throughout, what we can actually write is Q, okay, Q which is actually going out from R2 should be equal to Q going out from any location R. So if this is actually R1 and this is actually any radius R, and it should be actually radius R2. Okay, the Q is actually going to be same throughout. Okay, so therefore we are actually saying if you are actually considering the radius between R1 and R, then also this equation should be actually same. Okay, basically we are actually saying the resistance, parallel resistance we are actually saying. So if you are actually considering the wall resistance or partial resistance, it should be actually same. Okay, so you got, so that's what it is actually written over here. Okay, so what we are actually saying is at R, okay, so T is equal to T. Okay, R is equal to R is equal to R, T is equal to T, R is equal to R2, T is equal to T2. Okay, so that is actually the only difference. So we are actually going to integrate it or equating it. So we actually say Q into 2 pi Lk T1 minus T2 divided by ln R2 by R1. Okay, so here we are actually consider the wall length. Okay, so therefore the wall resistance and the full temperature potential we are actually assuming. Okay, so if you are actually assuming only the half length or some other radius R, then we have to actually find only that potential and that resistance. Okay, so if you are actually doing that, then you are actually going to get 2 pi Lk T1 minus T divided by ln R by R1. Okay, yeah. So now everything you can actually do. So now you can actually cancel this 2 pi Lk you can actually cancel. Okay, then you are actually going to do this. You are actually going to get T is equal to you can actually take this one up over here. You can actually see that T1 minus T2 divided by ln R2 by R1 into ln R by R1. Okay, so this is actually same as equation 26a. Okay, so what is actually equation 26a? Equation 26a, yeah. So T1 minus T2 divided by ln R2 by R1 ln R by R1. Okay, so the same equation we actually got it over here. So this is actually the other method in which you can actually calculate the, or you can actually reduce the temperature profile. Okay, so this is actually one method, but this is also okay. So from here also you are actually going to get, so from this from the Q cylinder again you can actually reduce what is actually the thermal resistance ln R2 by R1 divided by 2 pi Lk. Okay, so likewise all the analysis further also you can actually do it over here. Okay, yeah. So any doubts in this? Okay, fine.
No, sir.
Very good. Yeah. So we can actually stop our class over here today. So tomorrow we will actually see the cylindrical system with heat generation. Okay, we will actually see on that, and we will actually go through the spherical system. We will start with the spherical system, and spherical system we will not be actually discussing very much. The same procedures we can actually follow. Okay, so whatever we actually discuss, either use the alternate method or the basic method, basic derivation method. Either use that, and you can actually do for the calculations for the spherical system. Okay. So that's what we will actually see for tomorrow. The cylindrical systems with the heat generation and spherical system. Okay, so if you don't have any further queries, then we can stop the class. Okay, then have a nice day to all.
Thank you, sir.
Yeah, bye.
Thank you, sir.
Thank you, sir.
Thank you.